Beneath the frozen surfaces of Saturn's moons, something extraordinary is happening. Enceladus is spraying material from a hidden ocean into space. Titan has rivers and seas made of liquid methane, and several of these distant worlds may contain the ingredients needed for life. These discoveries are changing what scientists thought they knew about the outer solar system. Before the journey begins, please like this video, subscribe to the channel, and join the exploration of Saturn's most mysterious icy moons. Saturn moves through the outer solar system as a world surrounded by rings, moons, dust plasma, and a region of gravitational influence. It travels around the Sun at an average distance of about 1,400,000,000 kilometers, where sunlight is far weaker than it is near Earth. From this remote orbit, Saturn receives only a fraction of the solar energy that reaches the inner planets. Its cloud tops remain extremely cold, and the space around it forms a dim environment in which ice becomes a common building material. Water, ammonia, methane, and other volatile substances can remain frozen across many of the small worlds that circle the planet. Saturn is the second largest planet in the solar system. Its equatorial diameter reaches almost 120,000 kilometers, while its rapid rotation gives the planet a visibly flattened shape. Beneath the upper clouds lies a thick atmosphere made mainly of hydrogen and helium. Deeper layers become denser and hotter until the gases behave more like fluids under pressure. Below the visible surface, a region of heavier material is thought to contain rock ice and compressed compounds mixed through the interior. The exact structure remains under study, but measurements of gravity show that Saturn is not arranged in sharply separated shells. The planet's gravity organizes a family of orbiting bodies. A large family of confirmed moons moves around Saturn, while the total changes as objects are discovered and their paths are verified. Some moons are large enough for gravity to pull them into rounded shapes. Others are irregular fragments only a few kilometers across. Their orbits extend from paths close to the outer edge of the atmosphere to distant routes millions of kilometers away. Together they form a system rather than a collection, because each moon responds to Saturn, the rings nearby moons, and the pull of the Sun. Saturn's rings occupy the central part of this system. They spread across hundreds of thousands of kilometers, yet most sections remain remarkably thin compared with their width. The rings consist mainly of water ice, with particles ranging from grains to blocks as large as buildings. Darker rocky material and organic compounds are present in smaller amounts. Particles follow individual orbits, but collisions and shared gravity shape them into bands, gaps, waves, and narrow structures. The rings do not form a solid sheet. They are a moving disk of separate pieces, each traveling around Saturn according to distance from the planet. Several moons orbit within or beside the rings. Their gravity clears gaps, confines narrow bands, and produces ripples. Some collect ring particles on their surfaces, while others release material after impacts. This exchange makes the boundary between ring and moon less distinct than it first appears. A moon may shape a ring while the ring alters the moon. Fine ice spreads outward from sources elsewhere in the system and settles across surfaces that would appear darker. Saturn's surroundings are linked by continuous movement, even when the visible landscape seems silent and still. Beyond the main rings, larger icy moons travel along nearly circular paths close to Saturn's equatorial plane. Their densities show that most contain mixtures of frozen water and rock. Some are dominated by ice, while others hold more rock. Their surfaces record craters, fractures, ridges, plains, and deposits formed under different conditions. Each moon's appearance depends on its size, temperature, composition, impact history, and orbital relationship with Saturn. Even neighboring moons can develop different landscapes because their interiors and motions are not identical. Orbital resonance plays a role across the Moon system. A resonance occurs when two orbiting bodies complete their paths in a numerical rhythm. Repeated gravitational pulls then occur at similar positions, slowly changing orbital shapes and internal stresses. These effects can preserve orbital differences over time. They can also produce flexing inside a moon. The system behaves like a network of repeated motions with gravity, passing energy and angular momentum from one orbit to another. The changes are often gradual, but they can shape surfaces and interiors over immense time. Saturn surrounds itself with a magnetosphere, a region controlled by the planet's magnetic field. This field is generated deep inside Saturn by moving electrically conducting material. The magnetosphere traps charged particles and guides them along paths. It rotates with the planet and interacts with the solar wind, the stream of particles flowing outward from the Sun. The region extends far beyond many moon orbits and creates a plasma environment around icy surfaces. Plasma is a gas in which some atoms have separated into charged particles. These particles can strike moon surfaces, alter exposed molecules, and release material. The magnetic field is closely aligned with Saturn's rotation axis. This near alignment makes the field different from those of other giant planets and complicates measurements of Saturn's internal rotation. Within the magnetosphere, moons act as obstacles and sources. They absorb charged particles, disturb flowing plasma, and add neutral gas or dust to the surrounding space. Saturn's radiation environment is milder than Jupiter's intense regions, but it still changes the upper layers of exposed ice. Over time, energetic particles can break chemical bonds, create new compounds, and darken or brighten local materials. Sunlight also shapes the system, although it arrives weakly. Ultraviolet radiation can alter surface molecules and thin gases. Micrometeoroids strike rings and moons, producing dust and exposing cleaner ice beneath weathered layers. Saturn's gravity captures some particles and removes others. The solar wind presses against the magnetosphere, causing its sunward side to compress and its nightward side to stretch into a long tail. Every orbit passes through a setting influenced by these forces, but the strength of each effect changes with the distance, position, and time. Seen as a whole, Saturn's moon system is an extended icy environment held together by gravity and continually modified by collisions, radiation, orbital rhythms, and drifting material. The arrangement remains in constant motion. The rings occupy its bright central plane, while rounded moons and irregular fragments spread across a much larger volume. No single boundary marks where the system truly ends. Saturn's influence fades gradually into interplanetary space, where the Sun and neighboring bodies become more important. Within that broad domain, frozen worlds preserve evidence of formation, disruption exchange, and long-term change under the quiet conditions of the outer solar system. Far beyond Saturn's bright rings and large inner moons, a scattered population of small bodies travels through the planet's outer gravitational domain. These distant moons are called irregular satellites because their orbits differ from the orderly paths followed by the larger, rounded moons nearer Saturn. They move across wide regions, often along tilted, stretched or backward routes. Their paths reveal a history shaped by capture collision and long periods of orbital change. Each body is small, dark and difficult to observe, yet together they preserve evidence from the early solar system. Most irregular moons are only a few kilometers to a few tens of kilometers across. Their gravity is too weak to pull them into spheres, so they remain uneven in shape. Some may resemble broken rocks, while others may be loose collections of fragments held together by weak gravity. Their surfaces are expected to contain mixtures of ice rock and dark, carbon-rich material. Because they are distant and faint surface maps do not exist for most. Sizes are estimated from brightness and assumed reflectivity. The orbits of these moons extend millions of kilometers from Saturn. At such distances, the planet's gravity remains dominant, but the Sun exerts a stronger relative influence than it does near the rings. Their orbital periods can last many months or several years. Some move in the same direction as Saturn's rotation, called a prograde orbit. Many others move in the opposite direction, known as a retrograde orbit. These backward paths indicate that the moons did not form in place within Saturn's original disk of gas and dust. Instead, they are thought to be captured objects. Capture requires a body to lose enough energy to remain bound to a planet. A simple two-body encounter cannot usually produce permanent capture because the object approaches and leaves with nearly the same energy. In the early solar system, gas around Saturn, interactions with other bodies or close encounters involving three objects could remove energy from a passing fragment. Once captured, the body could settle into a distant orbit. The exact process differs among models, and it remains uncertain which mechanism dominates, but observations indicate that capture occurs while the young Saturnian system is crowded and active. The irregular moons are often grouped into families based on similar orbits. Members of a family share related inclinations, distances, and orbital directions. These similarities suggest that each family may come from a larger captured parent body that later breaks apart. A collision can shatter such a parent into many fragments, and the pieces continue around Saturn along related paths. Over time, gravitational forces spread them apart, but their shared orbital pattern remains measurable. Saturn's outer moon system therefore contains traces of ancient breakups preserved through orbital motion. One broad family follows prograde paths at moderate tilts. Another group moves along more strongly tilted prograde orbits. A large retrograde population occupies wide and often elongated routes. Similarity within a group does not prove that every member shares one origin. Small objects can drift into nearby orbital regions, and observational limits can make relationships uncertain. Even so, the groupings help researchers study how captured bodies fragment and evolve. Phoebe is the largest well-studied irregular moon of Saturn. It travels on a retrograde orbit far outside the paths of the major moons. Unlike the bright icy bodies nearer Saturn, Phoebe has a dark surface and a density suggesting a mixture of rock and ice. Images from the Cassini spacecraft reveal an uneven world covered with overlapping craters, steep walls, ridges, and patches of brighter material. Some impacts expose ice beneath darker surface deposits. Phoebe's appearance and composition differ from those of Saturn's regular moons, supporting the view that it formed elsewhere before capture. Phoebe may originate in colder outer regions of the early solar system, where bodies rich in water-ice carbon compounds and other frozen materials accumulate. Its surface contains dark substances associated with primitive objects. These materials have changed through impacts and radiation, but they may retain chemical features inherited from an early stage of planetary formation. Phoebe is not preserved in an untouched state. Its battered landscape records repeated collisions, excavation mixing, and loss of material. It remains valuable because its composition may represent a population distinct from moons formed close to Saturn. Dust released from Phoebe and other distant bodies spreads through the outer Saturnian system. Micrometeoroid impacts strike their surfaces and eject tiny particles. Some material forms a vast faint dust ring associated with Phoebe's orbit. The ring is extremely diffuse and cannot be seen like Saturn's bright main rings. Its particles move mainly on retrograde paths. Sunlight affects the grains through a weak but persistent force, causing their orbits to change gradually. As they drift inward, some particles encounter larger moons and settle onto their surfaces. The outer irregular moons experience little internal geological activity. Their small sizes allow internal heat to escape early, leaving cold bodies without sustained melting or reshaping. Surface change comes mainly from impacts, radiation, and the slow movement of dust. Craters can remain for billions of years unless later collisions erase them. Temperature differences across their surfaces are modest compared with those near the Sun, but rotation and surface darkness still influence local heating. Dark material absorbs more sunlight, while brighter ice reflects more. These differences can affect exposed frost. Their orbits also change over long periods. Saturn's flattened shape, the gravity of larger moons, and the pull of the Sun produce gradual shifts in orbital orientation. Some paths remain stable for immense spans, while others can become chaotic. Collisions between irregular moons are rare in the present system, yet the orbital families indicate that major collisions occurred in the past. The surviving objects represent only part of an earlier population. Many fragments may have escaped Saturn, struck other moons, or broken into dust. At the edge of Saturn's domain, these small bodies define no sharp frontier. Their distant paths overlap a region where Saturn's hold weakens and solar gravity becomes increasingly important. They move through darkness as remnants of capture and disruption, carrying mixed ice and rock around the planet on tilted, elongated routes. Their faint surfaces and scattered motions preserve a record of Saturn's early environment when wandering bodies, gas collisions, and changing gravity built the distant architecture that remains today. Iapetus travels around Saturn at a great distance, following a broad orbit that separates it from the planet's brighter inner moons. Its path is unusual because it is tilted more strongly relative to Saturn's equatorial plane than the orbits of the large moons closer to the rings. This inclination gives Iapetus a distinct place in the Saturnian system. The Moon moves slowly across its long orbit, completing one circuit in about 79 Earth days. It rotates once during the same period, keeping the same hemisphere, generally facing the direction of motion. Iapetus is about 1,470 kilometers across, making it Saturn's third largest moon. Its low density indicates that water ice forms most of its interior, mixed with a smaller amount of rocky material. The surface is ancient, cold, and heavily cratered. Large impact basins overlap older scars, showing that Iapetus has endured collisions for billions of years. Little evidence suggests that broad areas have been renewed by recent internal activity. The Moon, therefore, preserves a long record of impact deposition erosion and slow change under weak sunlight. The most striking feature of Iapetus is the strong contrast between its hemispheres. One side is extremely dark, while much of the opposite side is bright with exposed water ice. The dark region is called Cassini Regio. It covers most of the leading hemisphere, the side that faces forward as Iapetus moves around Saturn. The trailing hemisphere remains much brighter and contains large areas named Roncevaux Terra and Saragossa Terra. The boundary between dark and bright terrain is irregular rather than smooth, and the contrast appears across crater walls, ridges, and low plains. The dark coating is not simply a different type of bedrock. Observations indicate that much of it is a relatively thin layer lying above brighter ice. Impacts, landslides, and steep crater walls expose pale material beneath the surface. The dark substance contains carbon-rich compounds and fine dust, mixed with altered ice and minerals. Its exact composition remains partly uncertain because remote measurements combine signals from materials that have been processed by sunlight-charged particles and micrometeoroid impacts. Even so, the broad source of the darkening is understood through the Moon's orbital environment. Dust from distant, irregular moons, especially material associated with Phoebe, drifts inward through the Saturnian system. Many of these particles move on retrograde paths opposite to the motion of Iapetus. When they cross its orbit, Iapetus meets them mainly on its leading side. The Moon, therefore, sweeps up more dust on the hemisphere facing forward. Over long periods, a thin coating accumulates and reduces the surface reflectivity. The process does not require a deep layer. A small amount of dark material can greatly change how much sunlight the ice absorbs. The difference in reflectivity creates a thermal effect. Dark ground absorbs more solar energy and becomes warmer than bright ice under the same weak sunlight. Although the surface remains very cold, the temperature difference is enough to influence the movement of water molecules. Ice on warmer dark areas slowly changes directly into vapor, a process called sublimation. The molecules travel across the surface and settle in colder regions, especially at higher latitudes and on the bright, trailing hemisphere. Over immense spans of time, this movement strengthens the original contrast. The dark side becomes darker as exposed ice is lost and non-ice material remains behind. The bright side becomes brighter as migrating frost collects there. This feedback does not create the initial dust pattern, but it amplifies it. The resulting appearance depends on both external coating and internal redistribution of surface ice. Crater interiors show this process clearly. Slopes facing warmer directions can lose frost, while colder surfaces preserve it. The pattern follows local sunlight surface angle and temperature, rather than simple geographic boundaries. Near the equator, Iapetus carries another unusual feature, a mountain ridge that extends across much of the Moon's middle. In some places, the ridge rises more than 10 kilometers above the surrounding terrain. It forms a long chain of peaks, plateaus, and broken segments. Several sections contain multiple parallel ridges rather than one continuous wall. Large craters cut through the structure, showing that the ridge is ancient. Its presence gives Iapetus a shape that resembles a walnut with a raised belt around its center. The origin of the equatorial ridge remains uncertain. One explanation proposes that Iapetus once rotated much faster. As its rotation slowed, the crust may have adjusted to a changing shape and produced compression near the equator. Another explanation suggests that a temporary ring forms around Iapetus early. Material from that ring may have fallen onto the equator, building a narrow belt of debris. Each model explains some observations, but faces difficulties. The ridge's exact history, therefore, remains unresolved, and its broken form preserves evidence that later impacts and slope failure modify it. Iapetus is not perfectly spherical. Its broad shape reflects an earlier time when the Moon is warmer and rotates more rapidly. As the interior cools, the icy shell becomes rigid. Tidal forces from Saturn gradually slow the rotation until Iapetus becomes locked, but the frozen exterior retains part of an older rotational bulge. This preserved shape indicates that the crust stiffens early and resists complete adjustment. The Moon's present form is therefore a record of cooling, as well as orbital evolution. Across the surface, steep slopes experience slow landslides. Ice and dark debris move downward along crater walls and ridge faces. Because gravity is weak, falling material can travel far before settling. Some slides expose brighter ice, while others spread dark deposits across lower ground. Impacts continue to excavate mixed layers and reveal contrasts between surface coating and underlying material. Radiation alters exposed compounds, but the low temperatures slow many chemical reactions. Iapetus remains a quiet world whose main changes occur through dust sunlight, impacts, and the movement of frost. Its two-toned surface is not a simple division between separate materials formed inside the Moon. It develops through an interaction between incoming particles and temperature-driven ice migration. Its rich ancient craters, preserved shape, and contrasting hemispheres hold a connected record of formation, cooling captured debris, and long surface exposure in Saturn's distant realm. Across this frozen landscape, every bright patch and dark deposit reflects a balance between inherited structure and slow environmental change over time. Hyperion moves around Saturn beyond Titan on an irregularly shaped orbit, carrying one of the most unusual surfaces among the planet's moons. It is not round. Its dimensions are unequal, and its body resembles a battered fragment rather than a settled sphere. The Moon measures roughly 360 kilometers along its longest axis and much less across the shortest. Its weak gravity cannot reshape the entire body into equilibrium. Instead, Hyperion preserves a form established by ancient impacts, internal structure, and the loss of material over time. The Moon's average density is very low, even for a body made largely of water ice. This low density indicates that Hyperion contains a large amount of empty space within its interior. It may be highly porous, with fractures, cavities, and loosely packed pieces extending beneath the surface. Rock and darker compounds are mixed with the ice, but the overall structure remains less compact than that of many other moons. Hyperion may be a remnant of a larger parent body that breaks apart, though its precise early history remains uncertain. Its exterior is covered with deep craters that overlap across nearly every visible region. Many craters have sharp rims and dark floors, giving the landscape a sponge-like appearance. The walls are steep and the depressions appear deeper than similar craters on denser moons. Hyperion's low gravity plays a major role in this shape. When impacts strike, much of the excavated material escapes instead of falling back across the surface. The crater remains open and deep, while loose debris does not build broad, softened blankets around it. The moon's porous interior also absorbs part of the energy delivered by impacts. Rather than transmitting strong shock waves across a solid body, the fractured structure compresses and collapses locally. This process can limit the spread of damage beyond the impact site. Craters therefore remain sharply defined, even when they form close together. Their walls may fail in small slides, but the overall terrain changes slowly. Hyperion lacks signs of broad volcanic resurfacing tectonic plains, or widespread melting that could erase its impact history. Dark material collects inside many crater floors. These deposits contain carbon-rich compounds and may include material related to dust found elsewhere in Saturn's outer system. Some of the dark substance arrives from external sources, while some may be concentrated from Hyperion's own mixed surface. Sunlight warms dark patches slightly more than surrounding ice. That difference can encourage nearby water ice to sublimate, leaving darker, non-ice material behind. Over long periods, the process deepens the contrast between pale crater walls and dark interiors. The dark deposits are not uniform layers covering the entire moon. They often lie in low areas where particles settle and where thermal conditions favor their survival. Impacts can expose cleaner ice beneath them, while later dust can gather again. Radiation from Saturn's magnetosphere and ultraviolet light from the Sun alter the chemistry of exposed compounds. These effects break some molecular bonds and create others. The resulting material becomes chemically complex, but observations do not determine every component with certainty. Hyperion rotates chaotically. Unlike moons that keep one face towards Saturn, it does not spin with a stable, repeating orientation. Its rotation axis changes and the length of a rotation varies. This behavior results from its irregular shape, stretched orbit, and gravitational interaction with Saturn and Titan. Saturn's pull acts differently on the moon's unequal sides, producing torques that disturb a steady spin. Small differences accumulate, preventing Hyperion from settling into a simple pattern. Chaotic rotation does not mean that the motion lacks physical rules. Gravity controls every change, but the outcome is extremely sensitive to small differences in position and speed. A tiny variation can lead to a different orientation later. The moon tumbles slowly, exposing changing regions to Saturn's sunlight and the surrounding particle environment. No fixed leading hemisphere consistently faces the direction of travel, so incoming dust and charged particles are distributed in a more complicated pattern than on tidally locked moons. Hyperion follows an orbital relationship with Titan. Titan completes several orbits while Hyperion completes a smaller number in a regular rhythm. This resonance helps maintain Hyperion's orbital shape and contributes to the forces affecting its rotation. Titan's gravity gives repeated pulls at related positions. The interaction does not make Hyperion's motion simple. Instead, it supports a stable orbital rhythm while the Moon's orientation remains unpredictable over long intervals. The surface temperature changes with sunlight and local reflectivity. Hyperion remains extremely cold, but dark crater floors warm more than bright, icy slopes. Because the Moon's orientation changes irregularly, patterns of heating also shift. Frost can move across very small distances as ice sublimates and later settles. However weak, gravity allows many released molecules and grains to escape. The surface, therefore, loses material more easily than larger moons, especially when impacts launch particles above escape speed. Close images from the Cassini spacecraft reveal ridges, pits, scarps, and crater walls filled with fine details. Some bright areas appear freshly exposed, while darker deposits lie in sheltered hollows. The texture suggests a fragile surface rather than solid bedrock covered by thick soil. Loose grains may rest at unstable angles because gravity is weak. Small disturbances can start slides, yet the falling material moves slowly and settles differently from debris on a larger world. Hyperion's irregular body, low density, deep craters, and chaotic spin are connected. A porous interior allows impacts to carve steep depressions without spreading damage widely. Weak gravity permits excavated material to escape. An uneven shape allows Saturn's pull to disturb the rotation. The changing orientation then alters how sunlight, dust, and charged particles reach the surface. Each feature influences the others, creating a moon whose appearance emerges from structure, motion, and environment together. Across Hyperion, ancient scars remain exposed with little renewal. The Moon does not conceal its history beneath smooth plains or fresh ice. Its dark pits and pale walls preserve a record of repeated impacts on a fragile, frozen body. Slowly tumbling through Saturn's outer system, it maintains a landscape shaped by emptiness within weak gravity at the surface and long exposure to space. Its quiet movement continues without a regular face or season, while every hollow ridge and fractured slope remains exposed to reshaping forces of Saturnian space across immense spans of time. Titan appears from a distance as a glowing sphere wrapped in orange haze. The ground remains hidden beneath an atmosphere that extends far above the Moon and blurs its edge. Titan is the only moon in the solar system with a dense atmosphere, and its air is thicker at the surface than Earth's. High above, however, the gas becomes thin cold and strongly influenced by sunlight, Saturn's magnetic environment, and particles from space. These upper layers form the starting region of Titan's atmospheric chemistry. Nitrogen makes up most of Titan's atmosphere. Methane is the next important gas, accompanied by hydrogen and small amounts of carbon-bearing and nitrogen-bearing compounds. In the highest regions, individual molecules travel long distances before colliding. The outer atmosphere gradually merges with space rather than ending at a sharp boundary. Some light molecules gain enough speed to escape Titan's gravity, while others are carried away by charged particles. This slow loss has continued over geological time and helped shape the atmosphere's present composition. Below the outer fringe lies the thermosphere, a broad region where sparse gas absorbs energetic sunlight. Temperature does not describe warmth there in the familiar sense because particles are widely separated. Individual molecules can carry considerable energy while the gas remains too thin to transfer much heat. Solar ultraviolet radiation breaks nitrogen and methane molecules apart. The fragments include atoms, molecular pieces, and charged particles. They begin reactions that build increasingly complex substances. Part of the thermosphere is an ionosphere, a layer containing many charged particles. Sunlight removes electrons from molecules on Titan's day side, while energetic particles from Saturn's magnetosphere can produce ionization on both sides. Titan spends much of its orbit inside Saturn's magnetic domain, yet conditions change as the Moon moves through flowing plasma and approaches the region's outer boundary. The ionosphere therefore varies with solar activity, local time, orbital position, and the surrounding particle environment. Cassini measurements reveal positive ions much heavier than the nitrogen and methane molecules from which the chemistry begins. They also reveal heavy negative ions, an unexpected population reaching masses associated with large organic structures. These ions are not living material. They are products of reactions in a cold atmosphere. Their importance lies in connecting small gas molecules with the first solid haze particles. Electrical charge helps fragments meet, remain together, and grow into larger clusters. The chemical network begins when energy splits stable molecules into reactive pieces. Carbon from methane joins hydrogen, nitrogen, and other carbon atoms. Step-by-step reactions form hydrocarbons, nitriles, and ring-shaped molecules. A hydrocarbon contains hydrogen and carbon, while a nitrile contains carbon and nitrogen joined in a characteristic group. Some products remain gases. Others combine into larger particles that no longer behave like ordinary molecules. The complete sequence is not fully known because many reactions occur at once, and some compounds are difficult to identify remotely. As newly formed particles descend, they collide and join into loose clusters. Laboratory studies suggest that Titan-like haze contains complex organic solids with varied structures rather than one substance. The name tholin is often used for laboratory material produced when energy acts on mixtures resembling Titan's gases. It is not a specific molecule. Titan's real haze may share properties with these experimental materials, but its composition changes with altitude, particle size, and chemical history. The upper haze forms several visible layers. A detached band can appear hundreds of kilometers above the haze, separated by a clearer region. Its altitude changes with season as Titan's global circulation responds slowly to the changing pattern of sunlight. The layer does not remain fixed because particles are produced, transported, and carried downward. Winds in the middle and upper atmosphere redistribute gases from warmer regions toward colder ones. Near a winter pole, descending air can concentrate chemical products that were created at higher altitudes. Titan's year lasts almost 30 Earth years. so each season continues for more than 7 Earth years. Atmospheric changes, therefore, unfold slowly. As the season shifts, the main circulation can reverse direction. Air rises in the summer hemisphere, moves across the moon at high altitude and sinks toward the winter pole. This broad movement carries newly produced compounds away from their source regions. Within the dark winter atmosphere, some gases become strongly enriched because descending air brings them from above, while weak sunlight slows their destruction. The orange color develops as haze particles absorb blue and ultraviolet light more effectively than longer wavelengths. Sunlight entering the atmosphere is scattered and filtered through the suspended material. From outside, the haze hides most surface detail at visible wavelengths and gives Titan a smooth appearance. Infrared radiation passes through certain atmospheric windows, more easily allowing instruments to examine deeper regions. In visible light, the layered haze remains the dominant feature, stretching around the entire moon and rising far above the solid body. Haze particles also influence temperature. They absorb solar energy in the upper atmosphere and block some sunlight from reaching lower levels. At the same time, gases and particles release infrared energy to space. The balance between absorption-emission chemistry and circulation determines the vertical temperature structure. Small changes in haze abundance can affect heating, while changes in temperature alter winds and condensation. The atmosphere therefore behaves as a connected system in which chemistry and motion continuously influence one another. Observations from Voyager Cassini. Huygens Earth-based telescopes and space telescopes show that Titan's upper atmosphere is active rather than uniform. Its density expands and contracts with solar conditions. Its haze layers shift with season. Its ions form large chemical structures, and its winds carry products across the globe. Important details remain uncertain, including exact pathways that create the largest particles and the rates at which material moves between layers. Even with these limits, the broad pattern is clear. Energy enters a nitrogen and methane atmosphere, breaks simple molecules apart, and supports a slow descent from gas fragments to complex organic haze. Above Titan, this process continues through darkness and weak sunlight. Molecules separate, recombine, gather electrical charge, and become tiny particles. Winds spread them. Gravity draws them downward, and radiation changes them along the way. The upper atmosphere remains a vast chemical region shaped by Saturn, the Sun, and Titan's own circulation, while its orange veil records the steady transformation of simple gases into increasingly complex matter. Titan's lower atmosphere carries methane through a cycle that resembles the movement of water on Earth, although the temperatures are far colder and the materials are different. Near the surface, nitrogen remains the dominant gas, while methane behaves as vapor cloud rain, liquid and ice. Sunlight provides limited energy, gravity draws rain downward, and winds move vapor across the moon. The result is an active weather system that reshapes parts of the landscape while leaving other regions dry for long periods. Titan's surface temperature remains near -179 degrees Celsius. At this temperature, water ice behaves like hard rock, while methane and ethane can remain liquid. Methane evaporates from lakes, and damp ground rises through the atmosphere and may condense when air cools. Clouds form when vapor gathers around tiny particles. Some clouds remain thin and short-lived, while larger systems can spread over broad regions. Their appearance changes with season, latitude, and local atmospheric motion. Most methane clouds occur in regions where air rises and cools. Near the summer pole, increased sunlight can warm the ground and encourage convection, the upward movement of buoyant air. Stronger cloud systems sometimes develop over lower latitudes after seasonal changes. These storms can produce intense rainfall over limited areas. The rain may continue for hours or days, then stop as the atmosphere returns to a more stable condition. Long, quiet intervals separate many of these events, especially near the equator. Methane rain falls onto a surface made largely of water ice mixed with organic material. Some liquid runs across the ground and gathers in channels. Radar images from the Cassini spacecraft reveal branching networks that resemble river valleys. Many begin on elevated terrain and lead toward lower plains or depressions. Their shapes indicate erosion by flowing liquid. Some channels appear broad and mature, while others are narrow and sharply cut. Their present activity varies, and many may remain dry between storms. In the polar regions, liquid collects in lakes and seas. The northern hemisphere contains the largest known bodies, including Kraken Mare, Ligeia Mare, and Punga Mare. Their dark radar appearance indicates smooth surfaces that reflect signals away from the spacecraft. The liquids consist mainly of methane and ethane with dissolved nitrogen and smaller amounts of other hydrocarbons. Shorelines form bays islands, narrow channels and flooded valleys. Some coastlines change as liquid levels rise or fall. The southern pole contains fewer large lakes at present. Seasonal differences may move methane between hemispheres over long periods, while variations in elevation and subsurface storage also influence where liquids remain. Titan's orbital cycle changes the strength and duration of sunlight received by each hemisphere. Northern summers are longer and milder, while southern summers are shorter and more intense. These differences may affect evaporation, rainfall, and the long-term distribution of lakes, though the complete balance remains uncertain. Some small polar lakes occupy steep-sided depressions with raised rims. Their shapes suggest that the ground has been removed or dissolved over time. On Titan, liquid hydrocarbons may slowly alter materials that contain organic compounds or other soluble substances. Repeated filling and evaporation can deepen depressions and leave deposits around their edges. The process has similarities to karst landscapes on Earth, where water dissolves rock, but Titan's chemistry, temperature, and materials create a different environment. Beyond the lakes, broad plains cover much of the surface. These regions show gentle relief and are composed of mixed icy and organic material. Some plains may form through the accumulation of sediments carried by wind, rain, or flowing liquid. Others may represent older surfaces softened by deposits. Radar brightness varies according to roughness and composition. Smooth ground appears dark, while rough terrain returns stronger signals. These patterns allow broad geological units to be mapped even where visible light cannot reach the surface. Near Titan's equator, vast dune fields stretch across thousands of kilometers. The dunes form long, nearly parallel ridges, often separated by lower corridors. They are built from dark organic grains rather than ordinary silicate sand. The particles may originate as atmospheric haze that settles, changes chemically, and becomes gathered by wind. Some grains may also form when surface materials are eroded and broken apart. Their exact composition remains uncertain, but observations indicate that they are richer in carbon compounds than the surrounding icy terrain. Titan's near-surface winds are generally gentle, yet occasional stronger gusts can move grains. The dunes record the combined effect of winds acting over long periods. Their orientation suggests that rare energetic events may control their shape more strongly than common weak breezes. Mountains, craters, and other obstacles redirect airflow, causing dunes to bend around high ground. The ridges can reach considerable heights, and their broad distribution shows that dry conditions dominate much of the equatorial region. Mountains and ridges rise above some plains. Their exposed material is consistent with water ice, which forms Titan's solid foundation. These highlands are not extremely tall compared with mountains on Earth, but they influence drainage and wind. Valleys cut between them and sediments collect in nearby lowlands. Impact craters also remain visible, although Titan has fewer obvious craters than many other icy moons. The dense atmosphere destroys smaller incoming objects and slows others, while erosion and deposition gradually hide older scars. Winds continuously move fine material across the surface. Rain carries particles into channels and basins. Liquids evaporate from open seas and leave heavier compounds behind. Along some shorelines, changing levels expose fresh ground, while elsewhere, waves may gently modify the edge. Direct evidence for large waves is limited, and many observed surfaces appear remarkably smooth. Local ripples may form during windy periods, but long-lasting rough conditions are not required to shape the coasts. Titan's weather operates slowly under weak sunlight, yet it remains capable of sudden change. A cloud can gather, release heavy rain, and darken the ground across a wide area. The surface then dries as methane evaporates or drains away. Seasonal circulation shifts cloud zones over many Earth years. Lakes expand or contract, channels wait between storms, and dunes preserve the direction of past winds. Across the frozen landscape, methane links atmosphere and ground in a continuing cycle of evaporation, condensation, rainfall, flow storage, and return. Its quiet repetition gives Titan a surface shaped by weather, even where cold conditions preserve each change across long geological intervals. Titan's landscape rests on a foundation of water ice that behaves as bedrock under the moon's extreme cold. At the surface, this ice is rigid and mixed with organic deposits delivered from the atmosphere. Beneath it lies a crust whose thickness and structure are not observed. Measurements of gravity as shape rotation and tidal response provide indirect clues. Together they indicate that Titan is not a solid frozen body. Its outer shell likely covers a deep layer of liquid water mixed with dissolved substances. The crust contains fractures, pores, and buried sediments. Methane rain can enter openings, while liquid hydrocarbons may collect in reservoirs. Organic particles settle from the atmosphere and become incorporated into surface materials. In low regions, flooding and drying can leave layered deposits. These features remain separate from the deep interior, yet they show that Titan's crust is not perfectly sealed. Material can move downward through cracks, impact damage, and zones weakened by stress. Below the layers, pressure rises steadily. Water ice can exist in crystalline forms, each stable under different conditions. The form found at the surface is called Ice 1. Deeper inside Titan, higher pressure may create denser forms whose molecules are arranged more tightly. Temperature rises with depth because heat remains from formation, radioactive elements decay within rocky material, and tidal forces contribute. The balance between pressure and heat determines where ice remains solid and where liquid can persist. Evidence for an underground ocean comes partly from Titan's response to Saturn's gravity. As Titan follows its orbit, the strength and direction of Saturn's pull vary. A fully solid moon would flex a limited amount. Cassini measurements indicate tidal deformation consistent with a liquid layer separating the outer shell from deeper material. This liquid allows the crust to move more freely. The exact deformation depends on shell thickness, ocean density, and internal structure, so several models can match the observations. Titan's rotation supplies a clue. The orientation of surface features changes in ways that may be easier to explain if the icy crust is partly detached from the deeper interior. Winds can transfer angular momentum to the shell, while Saturn's gravity resists the change. A subsurface ocean reduces the mechanical connection between the crust and the core. Measurements remain difficult and some estimates have been revised, but the evidence continues to support a liquid layer extending around much of the Moon. The ice shell may be tens to more than 100 kilometers thick. Its thickness may vary because heat does not escape evenly. Warmer regions can support thinner ice, while colder areas allow a thicker shell. Convection may occur within the deeper ice. In convection, warmer material rises slowly and cooler material sinks. Ice remains solid during this movement, but over geological time it can flow slowly like a very stiff substance. This circulation transports heat and may create stresses in the crust above. The hidden ocean is expected to contain water, ammonia salts, and dissolved compounds. Ammonia lowers the freezing temperature of water, helping liquids survive under cold conditions. Salts can have a similar effect and change the ocean's density and electrical properties. The composition remains uncertain because no instrument has sampled it. Gravity data and theoretical models suggest that the liquid may be denser than pure water. Its temperature depends on pressure and composition, but it remains far below the temperatures of most oceans on Earth. At the base of the ocean, a layer of high-pressure ice may exist. Titan's internal pressure can transform water into dense, solid phases beneath the liquid. If this layer is continuous, it separates the ocean from the rocky interior. Such separation limits chemical exchange between liquid water and rock. However, the thickness and continuity of high-pressure ice depend on Titan's thermal state and composition. Warmer models permit areas where liquid may approach rock, while colder models produce a stronger barrier. Observations do not determine which arrangement is correct. Titan's deep interior contains a mixture of hydrated rock minerals and water-rich material rather than a dry metallic core. During early formation, heating may have allowed partial separation between rock and ice. The degree of separation remains uncertain. If the interior never becomes fully melted, rock and water can remain mixed across a broad central region. Radioactive decay within rocky material continues to release heat slowly. This energy helps maintain the temperature structure that supports the buried ocean. Exchange between the deep interior and the surface may occur through cryovolcanism, a process in which water-rich liquid or soft ice rises instead of molten rock. Some mountains, flows, and features on Titan have been proposed as cryovolcanic landforms. Their origin remains debated because erosion, sediment deposition, and tectonic movement can create similar shapes. No eruption has been confirmed. If cryovolcanism occurs, it may bring water ammonia and dissolved material upward where the liquids freeze rapidly in Titan's cold environment. Large impacts can also connect different levels of the crust. An impact may fracture the ice melt part of the target and create temporary pathways for buried material. Meltwater can remain liquid for a limited time beneath an insulating cover before freezing. Organic compounds from the surface may mix with this water. Such environments are local and temporary compared with the global ocean, but they demonstrate how surface chemistry can enter water-rich settings without crossing the entire ice shell. Tectonic stresses provide another possible route for movement. As the ocean freezes or melts, its volume changes and places pressure on the crust. Tidal flexing repeatedly bends the shell. Convection shifts material below. These processes can open fractures or compress older ones. Methane stored within the crust may escape along weakened zones, while water-rich material may rise part way before freezing. The rates of these exchanges remain uncertain and may be extremely slow. Beneath Titan's dunes, plains, lakes, and icy mountains, the interior remains layered and mobile on geological timescales. A rigid surface gives way to warmer flowing ice, a deep liquid ocean, possible high-pressure ice, and a rock-rich center. Gravity and rotation reveal this hidden arrangement without exposing it directly. The buried ocean persists because pressure-dissolved compounds and internal heat prevent complete freezing. Titan, therefore, carries a concealed water reservoir beneath an outer world shaped by methane, with its internal boundaries controlled by cold pressure and the gradual movement of heat. Rhea moves around Saturn as a pale, heavily cratered moon, whose surface records a long history of impacts and slow modification. It is the second largest of Saturn's moons after Titan, with a diameter of about 1,528 kilometers. Its nearly spherical shape shows that gravity has been strong enough to pull the body into equilibrium, yet its low density indicates that water ice makes up most of its mass. Rock is present in a smaller proportion, mixed through an interior that has remained cold for much of its history. The surface reflects sunlight strongly because exposed water ice covers large areas. From a distance, Rhea appears bright and relatively uniform, but closer images reveal terrain marked by countless craters, narrow fractures, broad plains, and subtle differences in brightness. The abundance of craters shows that much of the crust is ancient. Large and small impacts overlap one another, creating a layered record in which younger scars cut across older ones. Very little widespread resurfacing has erased this record, so the Moon preserves evidence from the early Saturnian system. Impact craters dominate nearly every region. Some are simple, bowl-shaped depressions, while larger examples contain central peaks, collapsed walls, and broad ejecta blankets. Ejecta is material thrown outward during an impact. On Rhea, this material can spread across the icy ground and later become altered by radiation and smaller collisions. Bright rays around some younger craters indicate fresher ice exposed from below the surface. With time, these rays fade as micrometeoroids and charged particles change the texture and chemistry of the uppermost layer. Rhea's largest impact structures reach several hundred kilometers across. Their formation releases enough energy to fracture the crust deeply and redistribute enormous amounts of ice. Some old basins are difficult to identify because later craters cover their rims and floors. The largest impacts may have affected the interior as well as the surface, but no clear evidence shows that they triggered long-lasting global geological activity. Instead, the Moon appears to have absorbed repeated collisions while remaining mostly rigid and cold. One hemisphere contains bright, wispy markings once interpreted as deposits of fresh material. Cassini images reveal that these markings are mainly steep ice cliffs and fracture walls. Their brightness comes from exposed clean ice rather than from broad blankets of erupted material. The fractures form networks that cut across older cratered terrain. Some extend for hundreds of kilometers, suggesting that the crust once experienced large-scale stresses. Their shape is consistent with tectonic movement in which sections of the ice shell crack and shift without melting completely. These fractures may form as Rhea's interior cools and changes volume. If part of the internal water freezes, the resulting expansion can place the outer shell under tension. Tidal forces from Saturn may also contribute, although Rhea's present orbit produces less intense flexing than that experienced by more active moons. Ancient orbital conditions may have differed, allowing stronger stresses in the past. The precise timing remains uncertain, but the fractured terrain is older than many craters that lie across it, indicating that major tectonic activity ended long ago. Some regions appear smoother than the most heavily cratered ground. These plains may have formed through the movement of icy material, the burial of rough terrain by impact debris, or a period of limited resurfacing. No clear evidence confirms extensive cryovolcanic flows. The boundaries between terrain types are often subtle, and later impacts have modified them. Rhea, therefore, presents a surface shaped mainly by impacts with tectonic fractures and local smoothing, adding smaller chapters to the broader history. The upper crust is continually altered by Saturn's magnetosphere. Charged particles strike the ice, break molecular bonds, and produce new chemical arrangements. Water molecules can separate into hydrogen and oxygen-bearing fragments. Some products escape while others remain trapped in the surface. Ultraviolet sunlight and incoming dust add further changes. This processing affects only a thin layer, yet it can modify color reflectivity and composition, enough for spacecraft instruments to detect differences across the Moon. Rhea carries an extremely thin exosphere, a sparse collection of molecules surrounding the surface. It is not a dense atmosphere because particles rarely collide and can easily escape. Cassini measurements identify oxygen and carbon dioxide near the Moon. Oxygen can form when energetic particles strike water ice and release molecules from the surface. The source of carbon dioxide is less certain. It may involve carbon-bearing material within the ice chemical reactions driven by radiation or particles delivered from outside Rhea. The exosphere changes as particles are created and lost. Some molecules return to the surface, some are swept away by Saturn's magnetic environment, and some escape into space. Because Rhea's gravity is weak and the temperature is low, the gas remains extremely sparse. It cannot support weather clouds or winds. Its presence instead shows that surface ice is chemically active under constant bombardment, even though the landscape appears geologically quiet. Measurements of Rhea's gravity and rotation suggest an interior that is not strongly separated into distinct layers. Rock may be distributed through a large icy body rather than concentrated into a compact core. However, the internal arrangement remains uncertain because available data are limited. Models allow different degrees of separation between rock and ice. A small rocky center may exist, but Rhea does not show the strong internal activity expected from a warm, rapidly evolving interior. Early in its history, Rhea contains more heat from formation and radioactive decay. Some internal melting may occur, allowing limited movement of water and rock. As heat escapes, the moon cools, the crust thickens, and the interior becomes increasingly rigid. Any liquid water that once exists is expected to freeze over time unless salts or other compounds lower its freezing point. Current evidence does not require a global ocean beneath the surface, and observations indicate a largely frozen body. Rhea's ancient crust, therefore, remains a quiet archive. Craters record collisions, fractures record internal stress. Bright walls expose cleaner ice, and the thin exosphere records ongoing surface chemistry. Across billions of years, the moon changes without broad renewal. Impacts continue, particles strike the ground and molecules escape while the overall landscape remains old, cold, and stable beneath Saturn's distant light. Its battered surface preserves that endurance in every overlapping basin, ridge, cliff, and quiet plain. Dionae travels around Saturn as a bright, rounded moon, marked by old craters and long networks of fractures. It is about 1,123 kilometers across and is composed mainly of water ice mixed with rock. Its density is higher than that of several neighboring icy moons, suggesting that rocky material forms a larger share of its interior. Much of Dionae's surface is heavily cratered. Large basins, smaller bowl-shaped craters, and overlapping impact scars cover regions. These marks show that ancient terrain survives across much of the moon. Some craters have softened rims and shallow floors, while others remain sharp and bright. Differences in shape reflect age, local crust strength, and later modification. Fresh impacts expose cleaner ice beneath the weathered surface, producing bright rays that fade as charged particles. Sunlight and micrometeoroids alter the uppermost layer. The most distinctive features are bright lines and curved streaks that cross the trailing hemisphere. Early, distant images make them appear like deposits lying on top of the ground. Closer observations from the Cassini spacecraft show that they are cliff scarps and fracture walls made of exposed ice. Sunlight reflects strongly from these steep faces, creating narrow, bright markings against darker, older terrain. The fractures cut through cratered plains, demonstrating that tectonic activity occurs after much of the impact record is already established. Many fractures belong to broad systems of parallel troughs. A trough forms when the crust is pulled apart and a block of ground drops between faults. On Dionae, these structures can extend for great distances. Some are narrow and sharply defined, while others form wide valleys with multiple steps. Their geometry indicates tension within the ice shell. The crust does not crack at random. Regions stretch in organized directions, producing long fault zones that reshape earlier landscapes. The source of this tension is linked to changes inside the Moon and to gravitational forces from Saturn. As internal water freezes, it expands and can push outward against the crust. Cooling can also create stresses as different layers contract at different rates. Tidal forces deform Dionae as it moves through Saturn's gravity. Its orbit is nearly circular, so tidal flexing is limited, but earlier orbital conditions may have produced stronger deformation. A more elongated orbit would cause changing gravitational pull during each circuit, allowing the interior to bend and heat more strongly. Dionae participates in an orbital resonance with Enceladus. Dionae completes one orbit while Enceladus completes two. Repeated gravitational interactions maintain the relationship and influence both moons' orbital evolution. In the past, this resonance may help increase Dion's orbital eccentricity, a measure of how much an orbit differs from a circle. Greater eccentricity would increase tidal flexing and generate internal heat. The amount and duration of this heating remain uncertain, but it offers a plausible source for ancient tectonic activity. Some plains on Dionae appear smoother and less cratered than surrounding regions. These areas may represent surfaces that are younger or more strongly modified. Ice may have moved across them through slow deformation, or material may have risen from below and spread before freezing. Impact ejecta can also bury rough ground and create smoother textures. No active flow has been observed, and the origin of each plain remains uncertain. Their reduced crater density nevertheless indicates that parts of the surface experience renewal after the oldest terrain forms. A prominent fracture system called Padua chasmata cuts across the Moon in bright bands. Another named Palatine chasmata forms steep scarps and branching valleys. These structures reveal that the outer shell is brittle near the surface but capable of broader movement below. Faults can expose clean ice from depths protected from radiation and dust. Over time, cliff faces may crumble, producing bright debris at their bases. Small landslides soften some slopes while leaving the larger tectonic pattern intact. Dionae's craters also record crustal differences. Some large craters show central peaks formed when the icy ground rebounds after impact. Others contain fractured floors, terraces, or collapsed walls. In regions affected by tectonic movement, faults cross crater rims and divide old impact structures. This sequence allows relative ages to be established. A crater cut by a fault is older than the fracture, while a crater lying cleanly across a fault is younger. The surface is continuously processed by Saturn's magnetic environment. Energetic particles strike the water ice and alter its molecular structure. Hydrogen can escape more easily, leaving oxygen-bearing products behind. Carbon-rich material delivered by dust or impacts can react with the irradiated ice. These changes occur mainly within a shallow layer, yet they influence color and spectral measurements. DNA also carries a very thin exosphere containing oxygen molecules. It is produced when energetic particles release material from the surface, and it is far too sparse to support weather or protect the ground. Gravity measurements suggest that DNA is internally differentiated, meaning that denser rock has moved toward the center while lighter ice remains above. A rocky core may be surrounded by a thick icy mantle and crust. Cassini data also permit the possibility of a deep subsurface ocean beneath the outer shell. Evidence includes gravity patterns and the way the crust responds to forces. The case is not as direct as it is for some more active moons, and the ocean's thickness, depth, and present state remain uncertain. If liquid water persists, dissolved salts and internal heat help prevent complete freezing. The ocean may lie far below the fractured surface separated from it by many kilometers of ice. Ancient tectonic features do not prove that the liquid exists today, but they show that DNA once contains enough internal energy to break and move its crust. Heat from radioactive decay, tidal flexing, and gradual separation of rock and ice may all contribute. DNA therefore presents a landscape where impacts and tectonics overlap. Old craters preserve early collisions, while bright cliffs record episodes of crustal stretching. Smooth plains mark limited renewal, and thin oxygen around the Moon records ongoing surface chemistry. Its present surface changes slowly, yet the long fractures remain clear evidence that the interior and orbit once reshape the ice on a global scale. These records remain visible beneath Saturn's weak and distant sunlight. Across the quiet Moon, every fault chasm crater and bright wall preserves part of that ancient mechanical history. Tethys moves around Saturn as a pale moon composed almost entirely of water ice. Its diameter is about 1,062 kilometers, and its low density shows that rock forms only a small fraction of its interior. The surface reflects sunlight strongly, yet close views reveal a landscape covered by craters, fault plains, and one enormous trench. These features preserve the record of a body that experiences violent impacts and large changes in its icy crust. Most of Tethys is ancient and heavily cratered. Small craters overlap larger ones, while broad basins contain later scars across their floors and rims. The density of impacts indicates that wide regions have remained exposed for billions of years. Some areas appear smoother. These plains may form when ice moves across low ground, when debris buries older relief, or when internal activity modifies the crust. Their exact origin remains uncertain, but they show that the Moon does not preserve one uniform surface age. The dominant impact feature is Odysseus, a basin about 450 kilometers across. It covers a large part of one hemisphere and is proportionally one of the largest craters. Its broad floor curves gently, and its rim is lower and less sharply defined than the rims of many younger craters. A complex group of central structures rises near the middle. The basin is so large that its formation affects much of Tethys and transmits powerful shock waves. Odysseus does not appear as a deep bowl. Its floor has relaxed upward since the impact. Water ice can behave as rigid rock near the cold surface, but over long periods it can flow slowly. This movement is called viscous relaxation. Warmer ice flows more readily than colder ice, so the present shape of Odysseus indicates that the interior retains more heat when the crater forms. The basin becomes shallower as deep ice shifts and supports the damaged crust above. The age of Odysseus is difficult to determine. Many smaller craters lie across its floor, confirming that it is ancient. However, it appears younger than some densely cratered terrain around it. Its creation may occur after Tethys has formed a rigid shell, but while deeper ice remains warm enough to deform. The impact excavates enormous volumes of material, fractures the crust, and possibly produces temporary melting near the center. Any liquid created by the event freezes as heat escapes. A second major feature, Ithaca Chasma, stretches across much of the Moon. This enormous trench is about 100 kilometers wide, several kilometers deep, and more than 1,000 kilometers long. It extends across nearly 3/4 of Tethys's circumference. The chasm is not a simple crack. It contains parallel scarps, stepped walls, long troughs, and raised blocks. Its scale shows that stress affects the crust globally rather than in one isolated region. Ithaca Chasma may form as the interior of Tethys freezes and expands. Water occupies more volume as ice than as liquid water. If an internal ocean or partly melted layer freezes, the Moon's volume increases and places the outer shell under tension. The crust responds by breaking and pulling apart. Large faults develop, and blocks of ice move downward between them. This process can create a rift extending around a major portion of the Moon. Another possibility links Ithaca Chasma with the formation of Odysseus. The impact sends waves through Tethys, and stresses may concentrate on the opposite side or along global fractures. Early interpretations suggest that the chasm could be a direct consequence of the collision. Later crater counts indicate that parts of Ithaca Chasma may be older than Odysseus, which weakens a simple impact origin. The relationship remains uncertain because different segments may have different ages and later events modify the original structures. The crust around Ithaca Chasma contains landslide slopes and impact craters cut by faults. These relationships allow relative ages to be reconstructed. A fault crossing a crater forms after that crater, while an impact lying across an undisturbed fault forms later. In some regions, crater walls break where the chasm passes through them. Elsewhere, younger craters interrupt the trench. The sequence suggests repeated movement rather than one brief fracture event. Tethys follows a nearly circular orbit. Tidal forces act on the body, but present flexing is limited because the orbit has little eccentricity. Earlier orbital conditions may differ. Resonances with neighboring moons can change orbital shape and increase internal heating for a time. The amount of ancient tidal heating remains uncertain, but it may help maintain warmer ice below the crust. Heat from formation and radioactive elements within the small rocky fraction also contributes. The Moon's bright surface is continually altered by charged particles and dust. Saturn's magnetosphere strikes exposed ice, breaks water molecules apart, and changes the uppermost layer. Micrometeoroids create small craters and scatter grains across the ground. Fresh impacts reveal cleaner ice, producing bright rays that slowly fade. Darker compounds occur in small amounts, but Tethys remains one of the most reflective bodies in the solar system because water ice dominates its surface. Tethys also interacts with faint ring material. Tiny particles can reach the Moon and settle across leading or trailing regions depending on their motion. Surface color varies subtly from one hemisphere to another, reflecting differences in bombardment and thermal conditions. These variations remain slight compared with the contrast seen on Iapetus. On Tethys, the main visual patterns come from relief shadow and the age of exposed ice. The interior is expected to be mostly frozen today. Its low rock content limits long-term radioactive heating, and its modest size allows heat to escape efficiently. A fully separated rocky core may not have formed, and rock may remain mixed through much of the ice. Evidence for a present global ocean is weak. Models generally describe a cold interior whose major geological activity belongs to the distant past. Across Tethys, Odysseus and Ithaca Chasma reveal two expressions of energy. One comes from an external collision that deforms a hemisphere. The other comes from stress that pulls the crust apart across immense distances. Their overlapping histories show how impact cooling freezing and slow ice flow shape a small moon. The present landscape remains silent and stable, while its cratered plains and enormous trench preserve the memory of a world once capable of global change. Enceladus moves around Saturn as a small, bright moon with a surface that reflects almost all incoming sunlight. Its diameter is about 504 kilometers, yet its southern region displays geological activity on a scale unexpected for such a modest body. Much of the moon is covered by old craters and smoother plains, but the South Pole differs sharply. Their broad areas contain few impact scars. Long fractures cross the ice and unusual warmth rises from below. These features show that the terrain is young and repeatedly renewed. The southern landscape begins near a boundary where older cratered ground gives way to broken plains. Ridges curve across the surface troughs cut through earlier features, and blocks of ice tilt against one another. The crust appears compressed in some places and stretched in others. This mixture indicates repeated deformation rather than one isolated event. Tidal forces from Saturn bend the Moon during each orbit, and the response is strongest where the shell is thin or already fractured. Enceladus follows a slightly elongated orbit. Its distance from Saturn changes during each circuit, so the planet's gravitational pull varies. The Moon stretches more strongly when it is closer and relaxes slightly when it is farther away. This repeated flexing generates friction inside the ice. The process is called tidal heating. Most of the energy is small when averaged across the whole body, but it can become concentrated within weak zones near the South Pole. Four major fractures dominate the southern terrain. They are informally known as tiger stripes because they appear as long, nearly parallel bands. Their formal names are Alexandria, Sulcus Cairo, Sulcus Baghdad Sulcus, and Damascus Sulcus. Each extends for roughly 130 kilometers, and the group crosses the pole in a regular pattern. The fractures are several kilometers wide, bordered by raised ridges and surrounded by terrain broken into smaller blocks and grooves. The tiger stripes are warmer than the plains around them. Cassini instruments detect infrared radiation emerging from the fractures, revealing heat far above the level expected from sunlight alone. The warmest zones lie along narrow parts of the fracture floors. Temperatures remain extremely cold by terrestrial standards, yet they are high enough to demonstrate a continuing internal energy source. The pattern also changes slightly, with orbital position linking the fractures to tidal stress. As Enceladus moves around Saturn, the cracks experience alternating tension and compression. Models indicate that the fractures open by small amounts during part of the orbit and narrow during another part. This movement is not a wide opening visible from space. It is a subtle mechanical change repeated over and over. Even small motion can grind ice, move warm material, and maintain pathways through the crust. The orientation of the stripes allows Saturn's pull to act on them efficiently. The ridges along the fractures rise several hundred meters above nearby plains. Some appear symmetrical, while others contain complex terraces and secondary cracks. Fine particles fall back onto the surface around them, creating bright deposits that soften older relief. The freshest material lies close to active openings, while more distant deposits become mixed with older ice. Repeated burial helps explain the shortage of craters in the South Polar region. Small impacts are gradually covered, and larger scars may be altered by tectonic movement. Beyond the main stripes, narrow faults form branching networks. Some cross-cut one another, revealing several periods of activity. A younger fracture interrupts an older ridge, while later deposits partly bury both. These relationships allow relative sequences to be reconstructed even without exact dates. The terrain does not form all at once. It develops through repeated cracking, shifting deposition, and renewal over long intervals. The South Polar surface is divided into blocks, separated by troughs. Some blocks resemble plates that have rotated slightly as the crust deforms. Others contain folded ridges suggesting compression. The combination of extension and compression may result from changes in the shape of the ice shell as tidal stress shifts through time. Global forces act on the crust, but local weaknesses determine where the movement becomes concentrated. Gravity measurements and the Moon's slight wobble indicate that the outer ice shell is not rigidly attached to the deeper interior. The shell can move over a liquid layer, allowing stronger tidal deformation. Near the South Pole, the shell may be much thinner than the global average. Estimates vary, but the active region is commonly modeled with only several kilometers of ice above liquid water. The exact thickness remains uncertain because no instrument directly measures the full fracture depth. Heat can travel upward through conduction, in which energy passes through solid ice and through movement of warmer material within the shell. Tidal flexing may also generate heat directly along faults. No single mechanism fully explains every observation. The measured warmth fracture motion and regional structure probably result from several processes operating together. Their balance can change as the shell thickness, orbital conditions, and internal circulation evolve. Saturn's gravity does more than heat the Moon, it also maintains Enceladus's orbital relationship with Dionae. The resonance prevents the orbit from becoming completely circular, preserving the changing tidal force needed for continued flexing. Without this relationship, internal friction would gradually reduce the orbital difference and weaken the heat source. The present activity, therefore, depends on a connection between Enceladus, Dionae, and Saturn. The South Polar region remains active today. Narrow jets emerge from particular sections of the tiger stripes, and their strength varies as tidal stresses change. The vents are not distributed evenly. Some locations remain more persistent than others, suggesting that fracture shape local temperature and access to deeper material control each source. The openings form part of a connected system rather than separate holes in otherwise undisturbed ice. Across this region, the surface records an ongoing exchange between orbital energy and frozen crust. Saturn bends the Moon. Friction produces heat fractures open and close, and fresh ice alters the landscape. Old craters disappear beneath deposits and deformation, while new faults cut across earlier structures. Enceladus remains small, but its south pole is dynamically young, mechanically active, and continuously reshaped by forces that act with each quiet orbit around Saturn. The bright polar ground therefore preserves not stillness but a delicate pattern of motion sustained beneath the distant light of the sun. Enceladus releases material into space from narrow vents along the south polar fractures. The escaping matter forms jets that combine into a broad plume above the Moon. Sunlight illuminates countless ice grains as they rise from the surface. Water vapor moves with them, accompanied by gases, salts, organic compounds, and mineral particles. This mixture allows spacecraft to examine material that has traveled through the active interior without drilling through the crust. The plume is not a uniform cloud. Individual jets emerge from distinct locations along the tiger stripes, especially from warm sections where fractures remain open. Some jets appear narrow, while others spread more widely. Their brightness and direction change as Enceladus moves around Saturn. Tidal forces alter stress along the fractures, allowing certain pathways to widen slightly and others to narrow. The plume responds to orbital position, although the strength of individual vents remains complex. Water vapor forms the main gaseous component. It expands rapidly into the near vacuum above the surface. As the gas rises, molecules separate and travel outward along paths controlled by their speed and Enceladus's weak gravity. Some fall back as frost, others escape the Moon entirely. The plume also contains carbon dioxide, methane, ammonia, hydrogen, and smaller amounts of additional gases. Their relative abundances vary between measurements and may change with vent conditions. Ice grains form when liquid droplets or water vapor freeze during ascent. Some particles are smaller than smoke grains, while others become visible through scattered light. Their shapes and structures reflect rapid cooling collisions and dissolved substances. Many grains contain nearly pure water ice. Others carry salts and organic compounds mixed with the water before freezing. The difference between particle types helps reveal pathways through the fracture system. Cassini passes through the plume several times and samples its material. Instruments detect particles by measuring mass speed, electrical charge, and chemical fragments after impact. The spacecraft also studies gases with mass spectrometers which separate molecules according to mass and charge. These encounters transform Enceladus into a world whose escaping material can be examined directly. The measurements remain limited by instrument range and resolution, but they provide a detailed chemical record. Sodium salts appear in a portion of the ice grains. These salts include compounds related to sodium chloride, sodium carbonate, and other dissolved minerals. Their presence indicates that liquid water interacts with rock or mineral-rich material before some droplets freeze. Salt does not enter vapor as easily as water molecules, so salty grains are more consistent with liquid spray than with sublimation from clean ice. The plume includes particles formed from water carrying dissolved material. Silica nanoparticles provide another clue. These particles are extremely small grains of silicon dioxide. Their size and structure can form when warm water reacts with silicate rock and later cools. Laboratory experiments show that certain temperatures and conditions allow silica to dissolve and then precipitate as nanoparticles. Cassini detects particles consistent with this process. The result points to mineral exchange within the water-bearing system, though the exact location cannot be measured directly. Organic compounds also occur in the plume. Some are simple molecules containing carbon and hydrogen. Others are heavier and more complex. Several ice grains contain concentrated organic material, suggesting that carbon-rich compounds gather at boundaries between liquid water and gas, or within bubbles. The exact structures of the largest molecules remain uncertain because spacecraft instruments break them into fragments during measurement. Even so, the fragments demonstrate chemical diversity. Molecular hydrogen appears among the gases sampled by Cassini. Hydrogen can be produced through reactions between water and certain minerals in rock. One process, called serpentinization, changes iron-bearing minerals and releases hydrogen. Other reactions may contribute. The observed abundance indicates that chemical energy is being generated and is not completely consumed before the gas escapes. The measurement identifies an active chemical imbalance, but it does not establish that any organism uses that energy. Ammonia in the plume helps keep water liquid at lower temperatures because it reduces the freezing point. Carbon dioxide and methane participate in additional reactions. Nitrogen-bearing and oxygen-bearing compounds add further variety. Phosphorus is present as phosphate within some ice grains according to analysis of Cassini data. Its presence expands the known inventory of dissolved material carried upward from Enceladus. Dust and gas do not rise forever in straight lines. Enceladus's gravity draws slower particles back to the surface where they settle as fresh frost. This falling material coats the south polar terrain and spreads across other regions. Faster grains escape into orbit around Saturn. Many become part of the E-ring, a faint ring extending beyond the main rings. Enceladus continuously supplies it while collisions, radiation, and orbital motion remove particles. The E-ring feeds material back onto several moons. Ice grains moving through the Saturnian system strike nearby surfaces and create coatings. Enceladus therefore alters itself and its surroundings. Neutral water molecules from the plume spread into a cloud around Saturn. Sunlight and charged particles break some apart or remove electrons, producing ions. These particles join Saturn's magnetospheric plasma and influence its composition and motion. The plume's output varies over time. Measurements suggest changes related to tidal stress, but simple opening and closing models do not explain every pattern. Gas and particle production may respond differently because they travel through fractures in different ways. Ice grains can collide with walls, freeze, melt, or become trapped, while vapor moves more freely. Seasonal lighting changes the visible plume, although it does not create the activity. Each rising grain carries a brief record of its journey. Salts record dissolved minerals. Silica records water rock reactions, organic fragments record carbon chemistry, and gases record pressure and temperature. The plume mixes these records before releasing them into space, so each particle cannot always be traced to one vent or depth. Even with that uncertainty, the combined evidence reveals a system transporting heat-water minerals and complex molecules through fractured ice. Above the South Pole, the plume continues as a quiet fountain. Some material falls back and renews the surface. Some joins Saturn's rings and plasma. Some passes through spacecraft instruments and becomes a chemical message from within the Moon. Through this escape, Enceladus exposes fresh matter to space and allows its hidden processes to be studied grain by grain, molecule by molecule across the cold environment surrounding Saturn. Beneath Enceladus's bright crust, a global ocean surrounds the Moon beneath a shell of water ice. Evidence comes from gravity, shell motion, south polar heat, and plume chemistry. No instrument has seen the ocean directly. Its presence is inferred from independent observations that fit one connected interior structure. The first clues arise from the Moon's slight wobble as it rotates. This motion is called libration. A frozen body would move with a smaller wobble because crust and interior would remain locked together. Cassini measurements show a larger response, indicating that the outer ice shell is separated from the deeper core. A liquid layer allows the shell to shift slightly as Enceladus follows its orbit around Saturn. Gravity measurements provide another line of evidence. During close flybys, Cassini experiences tiny speed changes caused by variations in Enceladus's gravitational field. These reveal how mass is distributed below the surface. The South Polar region contains more mass than expected from topography alone. A local sea can explain part of the signal, but measured libration requires liquid extending around the Moon. Together, the data support a global ocean with regional differences in depth. The ice shell is not equally thick everywhere. Models indicate thinner ice near the South Pole and thicker ice toward the equator and northern regions. Near active fractures, the shell may be only several kilometers thick. Elsewhere, it may extend for tens of kilometers. Exact values remain uncertain because they depend on density, temperature, salinity, and the rocky core's shape. A strong contrast between polar and global thickness remains consistent with observed heat and activity. The ocean itself may be tens of kilometers deep. Its water contains dissolved salts, ammonia, carbon dioxide, organic compounds, and mineral products from contact with rock. Salinity lowers the freezing point and changes water density. Ammonia helps liquid remain stable at lower temperatures. Pressure increases with depth, but Enceladus is too small to create thick layers of high-pressure ice between ocean and rocky interior. Liquid water can therefore remain in direct contact with the sea floor. Across the ocean, pressure and temperature vary with depth, latitude, tidal motion, salinity, and the changing thickness of the ice shell above each region. That contact is central to the Moon's internal chemistry. The rocky core is not expected to be compact, like a single stone. Measurements and models suggest a porous interior with fractures and connected spaces. Water can enter these openings, circulate through warm rock, dissolve minerals, and return carrying chemical products. This movement creates continuing exchange between water and the deep interior. Heat inside Enceladus comes mainly from tidal deformation. Saturn's gravity changes slightly during each orbit because the Moon follows a mildly elongated path. The resulting flexing bends the ice shell and deforms the rocky core. Friction converts movement into heat. A porous core may produce heat efficiently because grains, cracks, and water-filled spaces shift under stress. Energy can be released within rock and along fractures in the ice. The orbital resonance with Dionae helps preserve the slight elongation of Enceladus's orbit. Without this relationship, tidal effects would gradually circularize the path and reduce heating. The resonance exchanges orbital energy and allows flexing to continue. Heat production depends on internal structure. A rigid core generates less friction than a porous one, while a softer ice shell bends more easily than a colder, thicker shell. Heat moves from the core into the ocean and upward through the ice. Some energy travels by conduction, passing slowly through solid material. Some is carried by convection, in which warmer ice rises and colder ice sinks while remaining solid. Near the South Pole, liquid water and vapor can carry heat through fractures. These pathways concentrate energy below active terrain and help maintain thin ice there. The ocean is probably not still. Temperature differences, dissolved salts, and tidal forces can drive slow circulation. Warmer water may rise from the seafloor, while cooler water descends elsewhere. Salinity changes affect density and may create layered flow. Rotation can guide moving water into broad patterns. Direct measurements do not reveal the circulation, but moving water fits the transfer of heat and material from the rocky interior to southern vents. Hydrothermal activity may occur where water meets warm rock. Hydrothermal means that liquid is heated by the interior and reacts with minerals. Silica nanoparticles in plume grains support conditions in which warm water dissolves silicate material and later cools. Molecular hydrogen supports reactions between water and reduced minerals. These observations indicate ongoing water-rock interaction. Source temperatures, pressures, and shapes remain uncertain, and the evidence does not require large open vents like those on Earth's sea floor. The ocean's upper boundary lies beneath the ice shell. Water may fill fractures extending upward from the main liquid layer. As pressure changes, some water can rise, boil within low-pressure cracks, and separate into vapor and droplets. The droplets freeze into grains while gases continue upward. Salt can remain concentrated in liquid pockets, and ice may form along fracture walls. The passage is a changing network rather than a simple pipe. Tidal stress repeatedly changes the width and shape of these pathways. Fractures may open slightly, allowing pressure to fall and material to move upward. They may later narrow, trapping liquid or forcing it into nearby cracks. Heat prevents closure in active zones. Over time, channels can migrate, freeze, reopen, or become blocked by deposits. The ocean remains connected to the surface through dynamic crust, responding to every orbit. The age and long-term stability of the ocean remain uncertain. Enceladus may have been active for much of solar system history, or its present state may follow a recent period of enhanced heating. Models must account for energy needed to prevent complete freezing. A porous core, sustained resonance, and efficient tidal dissipation provide possible explanations. Observations establish liquid water today, but not how continuously it has persisted. Within Enceladus, the global ocean links orbit rock ice and plume. Saturn supplies tidal, forcing the core converts movement into heat. The water carries dissolved material and the shell directs part of it toward the South Pole. The ocean remains hidden, yet its mass shifts gravity. Its freedom allows crustal wobble, its heat warms fractures, and its chemistry appears in escaping grains. These connected effects reveal a deep liquid world enclosed beneath a small, frozen sphere. Enceladus's ocean contains more than liquid water. Material sampled in the plume reveals salts, gases, organic compounds, silica particles, and phosphate carried upward from the interior. Together, these substances describe an environment where rock-water heat and chemical reactions remain connected. Habitability refers to the ability of an environment to support life, as science understands it. It does not mean that life is present. It means that several basic conditions appear to exist in one place. Liquid water is the first condition. Beneath the ice shell, pressure and dissolved compounds keep a global ocean from freezing completely. The ocean remains in contact with the rocky core, allowing minerals to enter the water. This direct contact is important because rock provides elements and chemical surfaces that can participate in reactions. Unlike an ocean separated from rock by high-pressure ice, Enceladus's water can exchange material with the sea floor. The second condition is a source of energy. Sunlight cannot penetrate the thick ice, so surface light does not power the deep ocean. Energy instead comes from chemical differences and tidal heating. Saturn's gravity flexes the moon and generates heat within the core and shell. Warm water reacting with the rock can produce molecular hydrogen. This gas contains chemical energy because it can react with carbon dioxide or other compounds. On Earth, some microorganisms use similar reactions to obtain energy in dark environments. Molecular hydrogen detected in the plume indicates that water-rock reactions are occurring or have occurred recently enough for hydrogen to remain available. One likely process is serpentinization, in which water reacts with iron-bearing minerals and changes them into new mineral forms. Hydrogen is released during the reaction. The exact minerals and reaction rates inside Enceladus remain uncertain, but the measured gas supports a chemically active seafloor rather than a completely inert interior. Carbon dioxide and methane add further information. Methane can form through geological reactions involving hydrogen and carbon-bearing compounds. It can also be produced biologically on Earth, but its presence alone is not evidence of life. The relative amounts of methane, hydrogen, carbon dioxide, and other gases depend on temperature, pressure, rock composition, and reaction pathways. Current measurements cannot uniquely identify their source. They show that carbon chemistry is active and that several energy-producing reactions are possible. Organic compounds provide carbon-based material that can support complex chemistry. Cassini detects simple organics in the plume and heavier compounds within some ice grains. The largest structures are not fully identified because the instrument breaks them into fragments. Their presence shows that the ocean system contains molecules more complex than methane or carbon dioxide. Some may form through reactions between water and rock. Some may descend from material inherited during moon formation, and some may develop within the ocean itself. Nitrogen-bearing compounds are also present. Ammonia lowers the freezing point of water and can participate in chemical reactions. Other nitrogen compounds may contribute to the formation of amino acids or related molecules under suitable conditions. No amino acid has been confirmed in the plume. The available evidence identifies ingredients and pathways, not finished biological products. The distinction remains important because complex chemistry can arise without living systems. Phosphate detected in ice grains supplies phosphorus, an element used by known life for genetic material, cell membranes, and energy transfer. The inferred phosphate concentration may be high compared with many Earth oceans. This abundance can result from interactions between alkaline water and phosphate-bearing minerals in the core. The measurement expands the known chemical inventory of Enceladus, but it does not show how phosphorus is distributed throughout the ocean or whether it remains accessible in all regions. Sulfur has not been measured as clearly as several other elements yet. Models and meteorite comparisons suggest that sulfur-bearing compounds may exist within the rocky interior or ocean. Sulfur can support energy-producing reactions and contributes to proteins in terrestrial life. Its form and abundance remain uncertain. The habitability assessment therefore rests on confirmed water salts. Carbon compounds, nitrogen compounds, hydrogen, silica, and phosphate, with additional elements still under investigation. The ocean's acidity or alkalinity affects every reaction. Plume chemistry suggests that the water may be alkaline, meaning that it contains fewer free hydrogen ions than neutral water. Carbonate salts support this interpretation. Alkaline conditions can develop when water reacts with certain rocks. Such water remains compatible with some terrestrial organisms, although the exact value inside Enceladus is not directly measured. Temperature and pressure also vary, creating different chemical zones from warm seafloor pores to colder water beneath the ice. Silica nanoparticles indicate that warm water interacts with silicate rock and then cools. Experimental studies suggest that the particles can form under moderately high temperatures compared with the surrounding ocean. The exact range depends on chemistry and particle history. This evidence supports localized warm environments, not a uniformly hot ocean. Most of the water may remain cold, while fractures and porous rock contain warmer circulation. A habitable environment also requires stability over useful time scales. Chemical reactions need time to build complexity, and any organisms would need conditions that do not vanish immediately. The present ocean is active, but its age remains uncertain. Tidal resonance may sustain heating for long periods, while orbital changes may produce episodes of stronger or weaker activity. The ocean could be ancient and persistent, or it could pass through cycles of freezing and renewed melting. Current observations cannot distinguish these histories fully. Transport within the ocean influences habitability. Circulation can carry hydrogen and minerals away from the seafloor, bring oxidized compounds downward from the ice, and mix carbon-rich material through the water. If surface radiation creates oxidants in the ice and tectonic movement carries them downward, additional energy differences may develop. Evidence for this delivery is limited and the rate may be slow. Even modest transport could create chemically distinct environments. Enceladus therefore meets several major requirements associated with habitability. It contains liquid water, usable chemical energy, organic matter, dissolved salts, phosphorus, and ongoing water-rock interaction. It may contain warm seafloor regions and long-lived circulation. Yet, habitability is not detection. No observation identifies cells' metabolism, reproduction, or a uniquely biological chemical pattern. The ocean remains a chemically promising environment whose living status is unknown today. Its significance lies in the rare combination of accessible material and active internal processes preserved beneath ice and released naturally into space. The smallest particles escaping Enceladus carry the most detailed record of processes hidden beneath the ice. Each grain forms from water-dissolved salts, gases, minerals, and organic compounds moving through fractures above the ocean. Once released into space, the particle freezes, cools, and preserves part of that mixture. Spacecraft instruments cannot reconstruct every stage of its journey, but they can measure mass composition, charge speed, and the fragments produced when the grain strikes a detector. Some grains consist almost entirely of water ice. Others contain sodium salts, carbonate compounds, phosphate, silica, and carbon-rich material. These differences indicate that not all particles form in the same place or by the same mechanism. Nearly pure grains may condense from vapor, while salty grains are more consistent with droplets of liquid water that freeze during ascent. Organic rich grains may form where compounds gather at the surfaces of bubbles or within thin films near gas and liquid boundaries. Particle size also provides information. Very small grains can form through rapid freezing or direct condensation. Larger grains may grow through collisions, repeated freezing, or the breakup of droplets. Their size affects how easily they escape the vent, how far they travel, and whether they fall back onto the moon. A future spacecraft can compare size with composition, allowing different particle populations to be separated and connected to possible source regions. The structure of ice preserves temperature and cooling history. Water molecules can arrange themselves in different crystalline patterns. Rapid freezing may produce disordered ice, while slower cooling allows more organized crystals to form. Trapped gases and dissolved salts disturb these structures. Microscopic pores can hold volatile compounds that would otherwise escape. Examining crystal form, internal layering, and trapped bubbles can reveal whether a grain begins as liquid vapor or a mixture of both. Salts record the chemistry of the ocean and the minerals contacted by water. Sodium chloride points toward water, interacting with rock and concentrating dissolved ions. Carbonates reflect reactions involving carbon dioxide and alkaline conditions. Phosphate reveals that phosphorus enters the water from mineral sources. Ratios between these compounds may constrain acidity, salinity, temperature, and the amount of water-rock exchange. One grain cannot describe the whole ocean, but many grains can reveal repeated chemical patterns. Silica nanoparticles provide a finer mineral record. Their dimensions, shapes, and surface properties depend on how dissolved silica precipitates from cooling water. Laboratory experiments can reproduce particles under controlled temperatures, pressures, and chemical conditions. Comparing experimental grains with those from Enceladus can narrow the range of environments that produce them. The comparison remains indirect, yet it links microscopic mineral structure with processes occurring near the rocky core. Organic molecules offer a more difficult challenge. Carbon compounds can be simple or highly complex, and many form without life. Heat, radiation, mineral surfaces, and chemical reactions can build long chains, rings, and branching structures. A detector must therefore distinguish general organic richness from patterns that are unusually organized. The presence of a large molecule is not enough. Its arrangement, abundance, repeated subunits, and relation to surrounding compounds provide more meaningful evidence. Amino acids are one possible target. These molecules can form through non-living chemistry and are also used by known organisms to build proteins. Detecting them would expand the chemical inventory but would not by itself establish biology. Their relative abundances, structural preferences, and association with other molecules would matter. Known life uses particular handed forms of many molecules, a property called chirality. A strong and repeated imbalance in handedness could be significant, but non-living processes can also produce smaller imbalances. Lipids and related membrane-forming compounds provide another target. Some carbon molecules naturally gather into layers, droplets, or enclosed structures in water. Living cells use membranes, but simple membranes can assemble without life. Future instruments would need to measure chain lengths, branching patterns, and distributions rather than search only for one compound. A narrow repeated pattern may carry more information than a broad mixture produced by uncontrolled chemistry. Isotopes provide clues at the level of atomic mass. An isotope is a form of an element with a different number of neutrons. Chemical and biological processes can favor lighter or heavier isotopes by small amounts. Ratios involving carbon, hydrogen, nitrogen, oxygen, and sulfur can therefore preserve reaction histories. Geological processes also alter isotope ratios, so interpretation requires several elements and compounds measured together. A single unusual value would remain ambiguous. Possible signs of metabolism may appear as chemical disequilibrium. This condition exists when compounds that should react remain together in unexpected proportions because a process continually replaces them. Hydrogen, methane, carbon dioxide oxidants, and reduced minerals can form such relationships. Geological activity already creates disequilibrium on Enceladus. A biological interpretation would require patterns that known, non-living reactions cannot explain under measured conditions. Future missions can sample plume material at slower relative speeds than Cassini, reducing the destruction of fragile molecules during impact. Instruments with higher mass resolution can separate compounds that have nearly identical masses. Microscopes can examine grain shape and internal texture. Chromatographs can separate mixtures before analysis. Multiple flybys through different vents and orbital positions can test whether patterns remain stable or change with tidal stress. Contamination control remains essential. Spacecraft materials. Cleaning agents, fuel residues, and terrestrial microbes can produce misleading signals. Instruments must carry detailed records of substances used during construction and launch. Blank measurements can identify background contamination. Repeated detection in independent instruments strengthens confidence. Samples from different plume passages can show whether a compound belongs to Enceladus or to the spacecraft. The most reliable assessment would combine many small clues. Mineral particles would constrain temperature and water-rock reaction. Salts would describe the ocean's dissolved chemistry. Ice structure would reveal freezing pathways. Organic distributions, isotope ratios, and molecular handedness would test for unusual organization. No single measurement would carry the full conclusion. Agreement among independent patterns would provide the strongest evidence. Within each frozen grain, the ocean leaves only a partial imprint. The particle may mix material from different depths, strike a fracture wall, lose gases, or change as it freezes. Careful measurements must account for these alterations. Even so, the grains remain natural samples from an inaccessible sea. Their smallest structures preserve the closest available record of chemistry, heat, minerals, and possible biological processes operating beneath Enceladus's ice across long intervals of Saturnian geological time. Saturn's icy moons continue their quiet motion beneath the distant sun. Beyond the rings, dark captured fragments preserve the memory of early collisions. Iapetus carries dust across one hemisphere and bright ice across the other. Hyperion turns without a steady rhythm, holding deep craters in its porous body. Titan rests beneath an orange atmosphere where methane clouds gather rain, crosses frozen ground, and a hidden ocean remains sealed below thick ice. Closer to Saturn, Rhea, Dione and Tethys preserve ancient impacts, bright fractures, and immense scars formed as their interiors cool. Their surfaces change slowly under weak sunlight, charged particles, and the gentle fall of dust. Enceladus remains different. At its south pole, tidal forces open narrow fractures. Heat rises through the ice, and water from a buried ocean escapes into space. Each plume particle carries a small record of that hidden environment. Salts describe dissolved minerals. Silica points toward warm reactions between water and rock. Hydrogen reveals continuing chemical energy. Organic compounds show that carbon chemistry develops far below the surface. None of these observations proves that life exists, yet together they show that a small frozen moon can contain water, heat, rock, and complex chemistry in one connected system. The discoveries around Saturn do not turn the outer solar system into a familiar place. They reveal worlds shaped by conditions far colder, darker, and quieter than those near Earth. Their oceans remain hidden, their surfaces remain still, and their changes unfold across immense spans of time. Saturn continues to carry them through space, while rings, dust, gravity, and light link each moon to the wider system. In that slow movement, the icy worlds remain active, preserved, and waiting within the calm distance.